Okay, so we're still in section 12.5. So this is going to be, how do we define a plane that is passing through a point x naught, y naught, z naught with a normal vector ABC? Well, it's going to be defined through this equation right here. I've actually shown you all this equation when we talked about the dot product, okay? So the dot product says that, well, the dot product of two perpendicular vectors has to equal 0. So what is it really saying? If you have any vector that exists within this plane, okay, and we'll call this any point within the plane. That's x, y, and z. Okay. Now, remember that when we define vectors, it's going to be terminal point minus the initial point. So this vector that I'd be describing into this plane right here, the x, y, z, well, it'd be x minus x naught, y minus y naught, and z minus z naught. Okay? So if I did the dot product with that vector that I created from that point and the point that I already knew that existed within the plane, well, it would end up coming out to be 0. All right. So let's figure out a plane. So let's say find the equation of the plane . So we have a point in space, and we have a normal vector, which is going to be perpendicular to that plane. This is basically just follow up formula. So we would have 5 times x minus 3 plus 4 times y minus 2 plus 6 times z minus 1 is going to equal 0. Okay. And so that would give me 5x minus 15 plus 4y minus 8, 6z minus 6 is going to equal 0. Okay. So 5x plus 4y plus 6z is going to equal 15 plus 8 plus 6. Okay, so 15 plus 6 is 21. 21 plus 8 is 29. So that's 5x plus 4y, 6z equals 29. Okay. And that's it. That's the answer to the problem. Okay. So if you're given a normal vector and you're given a point, all you have to do is plug it into that formula. Now, what if we are not given a normal vector and just given points, like 3 points that are not in a straight line? If you have 3 points in a straight line, it's just going to form a line. Okay? If we have 3 points in space that are not in a straight line, well, that's going to form a plane. Okay? The plane passes through those 3 points. Okay? So let's say we want to find a plane that passes through, okay, I'm gonna label these, let's say P1, which is going to be 0, 1, 1. P2, go off the screen. Okay, where did P2? 1, 0, 1. And P3. Okay. So we have 3 points in space. Right? And I'm going to label them, let's do it like this. It doesn't really matter, but I'm going to put P2 right here. I'm going to put P1 right there, and I'm going to put P3 right there. Okay, I'm not actually drawing according to the axes of this one. I'm just saying 3 points in space. Okay. Okay. So if I describe the vector P2, P1. Okay. So that would be, right, so terminal point, initial point, that would be 0, -1. And then 1 minus 0, and then 1 minus 1. Okay. And now that would come out to be -1, 1, 0. Okay. Now let's say we had the other vector of P2, P3. Okay, so terminal point minus initial point, that will come out to be 1 minus 1, 1 minus 0, and then 0 and 1. That would come out to be 0, 1 minus 0 is 1, and then 0 minus 1 would come out to be negative. Okay. So from these 3 points in space, we can create 2 vectors. Actually, we can create 1. And then what we're going to do is we're going to do the cross product on these vectors to create a normal vector to that plane. Okay? So what we're trying to do is, let me draw it out like this. So we got some type of plane right here, and we want to create a vector that is going to be perpendicular to that plane. So, well, when I wrote it backwards in my notes, actually, you know what, I'll just change my notes. So, if I did, well, in my notes, I did P1 cross P2, that's my left hand. So the right hand rule says that if I do P2, P3 cross P1, P2, this is kind of arbitrary. That's going to make that one that sticks up like right there. Okay? So let's do P2, P3 cross P2, P1. Right. So this is what we're going to try to do. I'm deviating from my notes, but oh well. So this is going to equal the determinant of the matrix that I, J, and K, and I'm going with this one first, 0, 1, -1, and then -1, 1, and 0. Okay. So, this would equal I. Okay, so if I take the determinant of this thing, I is going to be associated with this guy right here. And so that's going to be 0 minus -1. Then minus j, okay, that would be 0. And then -1 times -1 is a positive 1, so that's going to be -1. And then plus k, okay. Taking the derivative of this guy over here, so that's 0 times 1, and then 1 times -1 is -1. So that would be 0 minus -1. Okay. So 0 minus -1 is just 1. Okay, so that would equal I, and then -1 into -1 plus j, and 0 minus -1 is also going to be positive, so that's going to be plus k. All right. So now we have a vector that is perpendicular to the plane that holds those 3 points. Okay? So, great. We got a perpendicular vector in this one. Okay? So, and now at this point of the problem, it doesn't matter which point you pick. It really is arbitrary. So let's say we just went with 0, 1, and 1. Okay? So, what do we know from this problem so far? What we know is that we have a normal vector call this A, B, and C, which is going to equal 1, 1, and 1. Okay? And then pick a point. Okay, it doesn't matter which point you pick. So let's say x naught, y naught, z naught equals 0, 1, 1. Okay, it's arbitrary which one you pick. Okay? And I can actually, I'll show you all in a second. You can pick any of them and you get the same answer. So, we would have 1 times x minus 0 plus 1 times y minus 1 plus 1 times z minus 1. All of this is going to equal 0. So, we have x plus y minus 1 plus z minus 1. All of that comes out to 0. And so now if I add 1 and 1 to the other side of the problem, I get to x plus y plus z. Is going to equal 2. You know, the reason I said this deviated from my notes slightly was I did the other cross product. And what did I get for the other cross product? If I did, instead of, what did I say, P2, P1, P2, P3 cross P2, P1. If you do P1 cross P2, P3, you'll end up with -1, -1, -1. That is the vector that's pointed the opposite direction. It's still perpendicular to the plane. And so if you did that problem, if you decided to do it in that way, you would end up with -x minus y minus c equals -2. It's the same equation. It's equivalent of just multiplying both sides of the equation by -1. So the equations that describe a plane are not unique in that sense, is that since this is just the equality right here, you can always multiply both sides of the equation by a constant, and it still describes the same plane.